Alright guys, so we have a quick problem to talk about. We want to find the slope of the tangent line on the volume of Descartes at the point 4/3, 8/3. Now, I haven't written the equation there yet. The equation of this, it's not a explicitly defined function. It's what we call an implicit function. That is, you gotta have x's and y's jumbled up together, and you can't really easily solve, or maybe at all, solve the equation for y. So I'll show it what I mean by that. We have the equation x cubed plus y cubed minus 6xy equals 0. So that's an implicitly defined function, because we can't solve it for y. We like to write equations as y equals something with x's in it. But if you try to solve this for y, you're going to have a hard time, because you could take this to the other side and that to the other side, but then you have y's on both sides. So at any rate, to avoid having to mess with any of that, we just have this thing called implicit differentiation. So we're going to implicitly differentiate and then find the derivative, find the slope of the tangent line, and maybe we'll find the equation of the tangent line too. For this particular problem, all we're really asked to do is find the slope of the tangent line. But maybe we'll take it a step further and find the actual equation of the tangent line. So this function has a graph like this. So notice it's not a, we call it an implicit function, but notice it's not a function in the fact that it doesn't pass the vertical line test. Clearly it's not a traditional function. Okay, so I just make sure we refer to this as an implicitly defined function. So if you graph a bunch of points, it looks like this: volume of Descartes. So it's like here we're just concerned in the first quadrant. If you continue the function, I believe you would get 3 petals actually, but we're just looking here at the upper right-hand petal in the first quadrant. So enough of that. Let's do implicit differentiation. So to do implicit differentiation, we take the derivative of both sides of the equation with respect to x. So you take the derivative of the entire right-hand side with respect to x. And you take the derivative of the entire right-hand side, which is just 0, with respect to x. Okay, and so now we have the properties of derivatives that say, hey, you can, if you have the derivative of several things added and subtracted, you can take the derivative of each of those individually. So we can write this as the derivative of x cubed with respect to x plus the derivative with respect to y cubed. Now you can do a couple things here. You can say minus the derivative, or you can take the derivative of the negative term. I'll just say minus the derivative of 6xy. And now, of course, we know the derivative of 0 is just 0, so we can go ahead and say that. Now, here's the key. The key is that if you take the derivative of a x term, then that's just business as usual. That's how we've always handled it. You're taking the derivative of a variable that a variable term that's a variable of x with respect to x. Nothing changes. So we're taking the derivative of x cubed with respect to x. So we know by the power rule that's just 3x squared. However, if we take the derivative of a y variable with respect to x, we have to use the chain rule. The chain rule says, okay, you take the derivative of the outside function, but then you multiply by the derivative of the inside function. So what we're doing there is we're saying, all right, let that be a function, okay, but imagine y is the inside function and x cubed is the outside function, okay? So the chain rule would say this. It would say take the derivative of the outside function, which would be 3 times something squared, but you evaluate that at the inside function, which is y. but then you multiply by the derivative of the inside function. Well, the derivative of the inside function, the derivative of y, with respect to x is just dy dx. So it turns out whenever you take the derivative of a variable term that's not x, or in this case y, you have to multiply by dy dx. So we took the derivative, kind of doing the same thing using the power rule, but since it was a y term, we had to multiply by dy dx. Now, here we have a x times y. That requires a product rule. So let's factor out that 6 actually, and put a -6 and then some brackets. Okay, so now we have, let's just maybe off to the side here, I'll erase it in just a few minutes. Let's look at x times y, the derivative with respect to x of x times y. Okay, so the product rule says you take the derivative of the first one, so that's the derivative of x times the second function, plus the derivative with respect to x of the second function times the first. That's the product rule. But, okay, the derivative of x with respect to x is just 1. So that's just 1 times y, or y. The derivative of y with respect to x, so the derivative of y would just be 1. But since we're taking the derivative of a y variable term, we have to multiply the derivative by dy dx, okay, according to the chain rule. So this is dy dx times 1 times x. So here is the derivative that goes in those brackets. So we put y plus, I'll rearrange it, x dy dx. And then we have equals 0. Okay? So we need to clean this up a little bit. Now the way implicit differentiation works is, once you take your derivative, you're trying to solve for dy dx. So treat dy dx like a variable. You're going to collect like terms, factor, and solve for dy dx. So first, though, we need to use the distributive property. We have 3x squared plus 3y squared dy dx minus 6y, okay, minus 6x dy dx equals 0. Now we're trying to solve for dy dx, so we're going to collect the dy dx terms on the left-hand side, take everything else to the right-hand side. So I'm going to leave this term on the left and that term on the left, take everything else to the right. So we're going to have 3y squared dy dx minus 6x dy dx equals, I'm going to, let's see, add 6y to both sides, subtract 3x squared from both sides. So negative 3x squared plus 6y. Okay? Now I'm trying to solve for dy dx, so I'm going to factor out my dy dx's on the left-hand side. That leaves me with dy dx times 3y squared minus 6x. The right-hand side, just leave it alone for the time being. But now to solve for dy dx, I simply divide by that set of parentheses. So I get dy dx equals negative 3x squared plus 6y over 3y squared minus 6x. So that is the implicit derivative. Notice, the implicit derivative has x's and y's in it. If it were possible, or if it were either possible or not too hard to do, we would want to rewrite this so that only x's were in there. But there's no good way to do that in this particular problem. Sometimes there's these nice substitutions you can make so that your final solution has only x's in it, but this is not one of those cases as far as I can tell. So this is our derivative. I guess we could simplify it slightly. Notice everything is a multiple of 3, so we could divide every term by 3. So we could do one little step here. We could say what? This is equal to negative x squared plus 2y over y squared minus 2x. Just divided everything by 3. Now, if that's the derivative, is the application, the interpretation of the implicit derivative is the same as the regular derivative. This gives the slope of all the tangent lines at all the ordered pairs on this curve. So instead of, with the regular explicitly defined derivatives, we just had to plug in x to find the slope above or below that x value. But here we have to plug in x's and y's, but we're given this point. So all we have to do is evaluate dy dx at this point. So it's going to be a little bit of arithmetic here. Let's see. So we need to take this function, or this implicit function, and evaluate it at 4/3, 8/3. So let's get a little. Actually, we don't need the bottom half here. We'll just do this. We'll do the arithmetic right here. So dy dx at 4/3, 8/3 equals, let's see, well, x is 4/3, so it's negative 4/3 squared plus 2 times y, which is 8/3, all divided by y squared, which is 8/3 squared, minus 2 times x, x being 4/3. Now let's see if I can do arithmetic today. All right, we're going to get 16/9, but negative 16/9 because there's a negative sign out front. Plus, okay, that's 16/3, just multiplying 2 times 8/3. This is squaring the top and the bottom, that's 64/9. Minus 8/3. So we don't have too much work to do here now. We just need a common denominator on the top, on the bottom, then combine those two fractions. All right, let's do this here. Okay, 16/3. If we get a common denominator, that's the same thing as what? 48/9, multiplying the top and the bottom by 3. So 48/9. If we want to get a common denominator down here of 9, multiply by 3 and 3, so that's 24/3. Let's see if I have enough room to solve this. Okay, this goes, okay, 16, negative 16 plus 48 would be negative 32. Or not negative, positive 32 rather. So that would be 32/9 for the top fraction. The bottom fraction is going to be what? 64 minus 24, so 40. Oh, typo. 24/9. So that is 40/9. Okay, now how do you divide a fraction by another fraction? You flip the divisor and multiply. So I'm sorry I'm out of space here. I'm going to try to squeeze it in here. This equals 32/9 times 9/40. Okay, almost done. 9's divide out. We're left with 32/40. What does that reduce to? Well, you divide the top and the bottom by 2, and you get 16/20. 16/20, then that is 8 over 10. Where's my brain all of a sudden? If you divide by, oh, what's wrong with me? I can't think all of a sudden. All right, I'm gonna my brain's not working all of a sudden. So this is 16 over 10. Nope, over 20, which is then 8 over 10, which is then 4 over 5. I'm not sure where my head was all of a sudden. I couldn't think for a moment to reduce that fraction, so I had to break it down. You can divide the top and the bottom by 8. All right, so here is the slope of the tangent line. Finally, we get equals m, 4 over 5. Now, I'm hoping all that work, I didn't make any little mistakes anywhere, 4 over 5. Now, that's all our question asked us to do, but let's get a little bit of practice in and do the one step further that we do a lot of, which is finding the equation of the tangent line at that point. It'll just take a few more moments. Let's get some more room though. I'll go over here. So once we have a slope m and we have a point, we can call it P, we can easily find the equation of the tangent line at P by simply doing a little bit of algebra. Remember, we have a point slope form, which is y minus y1 equals m times x minus x1. Okay, if this is x1 and that is y1, that's our slope. We just need to plug in, do a little bit of simplification, and we're done. So y minus y1 is y minus 8/3 equals m, which is 4/5, times x minus x1, which is 4/3. Now that is the equation, but that's the equation in point slope form. Typically we want the equation in slope-intercept form that is solved for y. So let's just go ahead and do that. So we can say y equals 4 over 5x, distributing here, minus 16 over 15, and then adding 8/3 to both sides. So all we have to do really is combine those fractions and we're done. So we could say y equals 4 over 5x. Let's see, the common denominator here, let's see, if we multiply the top and the bottom by 5, oh, we hit, let's see, we'll just do this, minus 16 over 15, plus if we do 15, 3 times 5, we get 15, 8 times 5, we get 40, and so we get y equals 4 over 5x. Let's see, if we just combine these, we get 24 over 15. So that's the equation of the tangent line at this point. So it'll look something like this. Of course, drawing by hand, you can't do the best job, but that's about what that'll look like. Does that make sense? Of course, our slope is positive. Okay, that's good. If we got a negative slope, that wouldn't have made any difference. Or that would have been a red flag for sure, because we know even if my graph isn't drawn perfectly, that slope of the tangent line has to be positive. Okay, so there we are. So let's recap real fast. We start with the implicitly defined function. We take the derivative with respect to x of both sides. Anytime you take the derivative of a y term, you have to multiply by dy dx according to the chain rule. Make sure to look out for product rules and more complicated computations. Once you take all the derivatives, you collect the dy dx terms on one side, everything else on the other side. Factor out the dy dx, in this case on the left-hand side. then divide by this factor to solve for dy dx. Do any type of simplification you can. Get this. Once you have the implicit derivative, if you want to find the slope of the tangent line, you plug in the x and y, because we need x and y here because our derivative is in terms of x and y. That will give us some arithmetic to take care of. Simplify here, be careful, get your final derivative. Just to be clear, we were done here as far as the homework problem was concerned. But I took it one step further and said, hey, if you want to find the equation of the tangent line, you simply, which we have to do often, we simply use point slope form from algebra class, plug in our point, plug in our slope, do a little bit of simplification, and there you are. And you, of course, you cross your fingers hoping that you didn't make a mistake anywhere. So, have any questions? Feel free to post on Blackboard, and I will certainly answer more questions. And if I need to make another tutorial, I certainly will. Talk to you soon.